Hey, this is a problem I thought I'd share with you guys. It's actually a very cool problem, simple, but it can be elusive sometimes. So here we have an officer who shines a light at a swimming pool which is 1.3 meters above the water surface. He's standing on the edge of the pool, and we're asked to determine the position or the location where the light beam hits the bottom of the pool. If the light beam strikes the surface of the water 2.5 meters away from the officer, and the bottom of the pool, we're told, is at a depth of 2.1 from the officer's feet. So let's sketch this out. I wanted to help you guys to learn how to treat problems. And as I always tell people, always square up with the problem. First determine the facts, what's given to you, and face head on what is required of you. And try to figure out what other things do you need to determine in the process of you responding to the question. Okay, so if we draw this out, here's our light ray. It hits the surface of the water, and we know due to the laws of refraction, it's going to change direction, and then there's going to be an angle of incidence and an angle of refraction. Now, if we're to determine the position where the light beam hits the surface or the bottom of the pool, because it's positioned, we need to determine two things, two coordinates. We need to determine coordinates, how far away from the officer in the horizontal and how deep. But because we know it's going to be at the bottom of the swimming pool, we already have some kind of a reference that from the officer's feet, it will be 2.1 meters because that's where the bottom of the pool is. So we have our y coordinate. And of course, your coordinate will depend on what you chose as your reference system. Actually, in this diagram, what I've chosen as my coordinate system is this red dot, where the the torch is. The torch is 1.3 meters above the officer's feet, which means the bottom of the pool is going to be 1.3 meters plus 2.1. But because my coordinate system, this is in the negative direction, then my y-coordinate of where the pool or where the light beam hits the bottom of the pool is going to be this value, negative the sum of 1.3 and 2.1, which is going to give us minus 3.4. So that is the y-coordinate. That's how deep from the position of the flash or the torch the light beam is going to hit the bottom of the pool. Okay, that's one coordinate. We haven't fully specified the position where the light beam is going to hit the bottom of the pool. So now we need to determine the x-coordinate. Well, it should be clear that the location where, along the x, the location where the light beam hits the bottom of the pool is going to be this distance here, plus whatever this distance is. Well, we know what this distance here is. That is from the edge of the pool to when the light beam enters the water. That's 2.5 meters. So the x-coordinate is going to be 2.5 plus this unknown part. This unknown part can be determined. So notice, although we were asked to find position, now we are narrowing our problem down. We have determined the y-coordinate. What stands in our way is this xl. This x sub l, or the x where the light beam hits the bottom of the pool, is now our new target. So how can we determine this xl? Well, this xl, notice, is actually the side opposite to the angle of refraction. So we know the adjacent side to this triangle. We know we can find this angle, but this is what we're interested in, the side opposite to that. Well, the trig ratio that relates these three things, this adjacent side, opposite side, and the angle, is the tan function. Now, taking the tan function, we can rewrite it this way and determine that xl, the position where the light beam is going to hit the bottom of the surface, is going to be given by 2.1 times tan of theta r. Now notice we have shifted our target from xl. We're no longer looking directly for XL. Now we know in order for us to determine XL, we need to find what theta R is. Theta R is related to theta I through Snell's law. So this then allows us to move our question from theta R to something else. And that's exactly what Snell's law teaches us, that theta R is actually dependent on the index of refraction for air and for water, together with the angle of incidence in this case. So then theta R is given by this new expression, which means we can determine theta R, but what's in our way? What's preventing us from knowing what theta R is? Well, it's theta I. Now we need to find ways of determining theta I. How can we find theta I? Well, notice theta I belongs to this triangle, and in particular, it is the angle opposite to the side which is 2.5 meters, and it's also the angle adjacent to another side, which we know to be 1.3. So we can determine theta I, and the way we do it is exactly using this trig function. Having found theta I, we can then plug it in here to find what theta R is going to be. When we find theta R, we plug it in there, and then when we have theta R, we can determine what XL is, and when we find what XL is, we can plug it in there in order to determine what the X coordinate is. This is how I encourage you to solve physics problems. Always face them head on and consider what is in your way to your goal. Initially, what was in our way was this XL, but we found out that in order to determine XL, we needed to find theta R. So then we moved our target to search for XR, and XR we found to depend on theta I. And when we found that theta I can be determined, this enabled us to unlock this puzzle. So I encourage you, just because you don't immediately have an idea of what to do with a problem, it doesn't mean it's undoable. Always fly by instrument. Ask the question directly, face it up directly, and work it backwards. Typically, by finding one thread, you can almost undo the whole thing. Okay, I hope that helps. If it doesn't, or if you have any more questions, please use the comment section, and hopefully I'll get back to you. Alrighty, see you in the next one.